started with the sheet though. Just a couple of more remarks on SHM, although these remarks are not required for the sheet, but these are pending remarks on simple harmonic motion. Now, think of a particle executing uniform circular motion. Uniform circular motion with angular velocity omega. Obviously, with constant angular velocity omega. And O be the center of the circle. And let's say A is the radius of the circle. A is the radius of the circle. At time t equal to 0, the particle is here. The particle is here at time t equal to 0. In t seconds, at an instant of time t, the particle arrives here. Call this particle P. So P at time t equal to 0, and this is P at time t equal to t. Particle is P, and it's executing uniform circular motion with angular velocity omega, the angular velocity omega. Now, in t seconds, therefore, the particle has gone from this end to this point, right? And it would have described an angle theta at the center. It would have described an angle theta at the center given by theta equal to omega t. Given by theta equal to omega t, because omega is constant. So in t seconds, it will describe omega t radians at the center. Now, for every position of P, you can conceive of its projection. You can conceive of its projection Q. So while P executes a circular motion, Q would oscillate along the extremities of this diameter. Q would oscillate along the extremities of the diameter. And there is a one-to-one relationship between the position of P and the corresponding position of. In fact, for every Q, you can identify a unique position P. You can identify a unique position P. Depending on the direction of motion. For example, while P goes in this direction, Q goes, while P moves in an anticlockwise sense, Q goes from this end to this end. Q goes from this end to this end. Now, say this is the origin of coordinates and this is the x direction. This is the x direction. Very clearly, the position of Q is going to be given by, say, x. The position of Q is going to be given by x at any given instant of time t. At an instant of time t, when P is here, its projection on this diameter, is right here. And if A is the radius of this circle, then the displacement of x with respect to O at any instant of time t is going to be given by this length, right? So x then is like a cos omega t. X then is a cos omega t. Or no, right? So despite the fact that the motion of P is really, really simple, it's uniform circular motion embracing constant angular velocity. The motion of Q as perceived by O is given by x equal to a cos omega t, which clearly is simple harmonic. So while P executes uniform circular motion, Q executes simple harmonic motion. the radius of the circle turns out to be the amplitude of motion of the angular velocity of P turns out to be the angular frequency of the simple harmonic oscillator Q. Yes or no? Right? So, while Q is here, P is here. When P is here, Q would be here, heading in this direction. P comes down here. Q comes closer and closer to this extremity. At some point of time, P is here. Q would still be here, but now it would move in this direction. Now it would move in this direction. So, while executing the upper half of the circle, while P executes the upper half of the circle anticlockwise, Q moves from right to left. And when P starts to execute the lower half of the circle in the anticlockwise sense, Q moves from left to right. That is what happens. That's what happens. Right? So, in fact, for every position of Q, you can think of two positions of P. One on the upper half of the circle, the other one on the lower half of the circle. So, when Q is moving from right to left, we might want to associate the corresponding point as P on the upper half of the circle. But in the event Q is moving from left to right, the corresponding point will be on the lower half of the circle and it would be heading in this direction. Yes or no? Right? So, depending on the position of Q, depending on the position of Q and the direction in which Q is heading, depending on the position of Q between these two extremities of the diameter and the direction in which Q is heading, you can uniquely identify the corresponding point on this circle, corresponding point P on this circle. Yes or no? Right? Not only that, say while Q goes from this Q to this Q, Q goes from this Q to this Q, P goes from this P to this P. Right? This P. Clear? So, the angle described by P, the angle described by P in a given time would be, for example, in this case, this is the angle described by P in a given time. And in that time, Q would have linearly described this length. Q would have linearly described this length. So, for every length that Q describes on this diameter, for every length that Q describes on this diameter, you can associate an angle theta that P describes at the center. Yes or no? Right? That is to say, when the projection Q goes from, let's say, Q1 to Q2, moving leftward, P goes from P1 to P2 on the upper half of the circle. O is the center of the circle. So, while Q would have gone from Q1 to Q2, P would have described an angle theta at the center. P would have described an angle theta at the center. And the time it takes for P to describe this angle theta is the time it takes for Q to go from Q1 to Q2, right? So, very clearly, what's the time taken by P to go from P1 to P2? Time taken by P to go from P1 to P2 is going to be, if you can find from geometry this angle theta, then the time it takes to describe this angle theta is going to be theta by omega. And in this time, Q would have migrated from Q1 to Q2 as shown in the figure, right? Even though we started with a particle executing uniform circular motion and concluded that its projection on a diameter executed simple harmonic motion, and that the angular frequency of oscillation of the simple harmonic oscillator, the angular frequency of oscillation of the simple harmonic oscillator was the same as the angular velocity of the particle executing uniform circular motion, we can look at just the inverse of the problem. We started with this and we associated Q with it. We could have done just the opposite, in the sense we could have started with a particle executing simple harmonic motion. We could have started with a particle executing simple harmonic motion, and let's say there was a particle executing simple harmonic oscillation between these two limits, Lm. There is a particle executing simple harmonic motion between extremities L and M. That means the midpoint of this must be the mean position of that oscillator. The midpoint of this must be the mean position of this oscillator. And half Lm must be the amplitude of oscillation. Half Lm must be the amplitude of oscillation. So we imagine a particle executing simple harmonic motion with angular frequency omega, and amplitude A, which is half Lm, right? Now, for the particle that is oscillating between these two extremities, L and M, I can jolly well, for this particle Q, which oscillates between L and M, I could jolly well associate a particle P. Which describes uniform circular motion, with angular velocity omega, same as the angular frequency of oscillation of the oscillator, and lying on a circle whose center is the mean position of the oscillator, and whose radius is the amplitude of oscillation. Yes or no? Right? This circle which is constructed with center as the mean position and radius equal to the amplitude of the oscillator, is called an auxiliary circle. This is a figment of our imagination. Right? The motion of Q is complicated. It's motion with varying velocity, varying acceleration, time varying velocity. Whereas its brother P, which moves on the circle, has a simpler motion to talk about, which is constant angular velocity, uniform circular motion, right? And since I can map the motion of Q onto P, it becomes easier for me to, it becomes really easy for me to describe the motion of Q or to find out various things about Q by looking at P. Instead of dealing with Q, I could actually deal with P. I mean, like I said, if I want to find the time Q takes to go from Q1 to Q2, I don't look at Q, the oscillator. I look at the corresponding point on the auxiliary circle. I call it the auxiliary point. The point on the auxiliary circle, I call it the auxiliary point, or the auxiliary particle, This has a much simpler motion. So while Q goes from Q1 to Q2, P goes from P1 to P2. And if I want to find the time it takes by the oscillator to go from Q1 to Q2, I don't deal with Q at all. I deal with P instead. P describes an angle theta at the center, like I said, and the time taken by P to traverse this arc is the time taken by Q to go from Q1 to Q2. So, and the time taken by P is simple, going to be theta by omega, and that's the time taken by Q to go from Q1 to Q2. So, instead of dealing with the oscillator, I deal with the auxiliary particle on the auxiliary circle, executing uniform circular motion with constant angular velocity omega. And all that I need to do is to deploy geometry to find this angle. So from geometry, if I can find the angle theta, then I can deal with the time it takes by time taken by Q to go from Q1 to Q2, right? Now, evidently then, say, there is a particle executing SHM between limits L and M with amplitude A and angular frequency omega. This then is the auxiliary circle centered at the mean position of oscillation and whose radius is equal to the amplitude of this oscillator, right? Now, while Q, let's say, starts from this point and P starts here, a full oscillation of Q is like going from M to L and then coming back to M. That's a full oscillation for Q, right? While Q executes a full oscillation, M to L and L to M, what does P do? P executes a full circle. Q going from M to L is like P executing the upper half of the circle, and then Q going from L to M is like P executing the lower half. And in a full cycle of oscillation, P would have described a full circle. And the time it takes for P to describe a full circle, that means describe an angle 2 pi radians at the center, that is an angle 2 pi radians at the center, is how much? Is 2 pi by omega. Which is also the time period of oscillation of Q. In fact, you could have started from any Q here, and let's say Q going this way, P going this way, and then for a full cycle of Q, what's required is you go from Q to L, P comes down here, and then L back to M, and in that time P would have described this arc, right? And then from M to Q, when Q goes, P goes from M to this P. That means a full oscillation of Q is always about a full revolution of P. A full revolution of P will be a full oscillation of Q. A full circle for P will be like a complete oscillation of Q. So there is a complete mapping between the state of motion of Q and position of P on the auxiliary circle as an auxiliary particle. Right? Now, say again we have an oscillator executing uniform circular oscillator which executes simple harmonic motion with angular frequency omega and amplitude A. And at some point of time, so this is the mean position, right? And the oscillator is heading in the rightward direction. So what about the corresponding point on the auxiliary circle? The corresponding point on the auxiliary circle is P, and it's moving like this. So while the oscillator Q goes from the mean position to this extremity, the corresponding point on the auxiliary circle goes from P to this. That means the corresponding point on the auxiliary circle describes a quarter of a circle. And if T is the time period for a full circle, which is like 2 pi by omega, then to describe a quarter of a circle, time taken by P to describe a quarter of a circle is going to be T by 4 seconds. And that's also going to be the time taken by Q to go from the mean position to the extremity. So the time taken to go from the mean position to the extremity would be 1/4 the time period, 1/4 the time period. And again, the time taken by Q to go from the extremity to the mean position. Even when Q is going from the extremity to the mean position, P goes from this extremity to this upper end. That means it again describes a quarter of a circle and the time taken will still be T/4. So whether you go from the mean position to the extremity or the extremity to the mean position, the time taken is going to be 1/4 the time period of oscillation, right? That's an important result. That's 1/4 the time period of the oscillator. Now, not only that, so let's say this R is the midpoint of OM. R is the midpoint of OM. Right? And the oscillator is at R at some instant of time. The oscillator is at R at some instant of time and is moving leftwards. The oscillator is at R at some instant of time and is moving leftwards towards the mean position. This is the midpoint of the amplitude. This is the midpoint of the amplitude and it's moving leftwards towards the mean position. Now, when the oscillator is here and is moving leftwards, the corresponding point on the auxiliary circle would be on this upper half of the circle at P, right? So while Q goes from the midpoint to the mean position, P goes from this point to this point, yes or no? Right? Now, this length is the radius, which is the amplitude of the oscillator, and this length is A/2. This length is A/2. Evidently then, this angle is 60 degrees. This angle, see, this by this is half. This length divided by this length is a half. So, this angle, theta, is 60 degrees. Pi/3, right? And therefore, P describes how much? P describes 30 degrees at the center. P describes 30 degrees at the center, that is pi/6, right? So, which means now, evidently, a quarter, the time taken to go from M to O is T/4, right? Now, for the corresponding point on the auxiliary circle, this 90 degrees could be divided into 330 degrees. So now, to describe complete 90 degrees at the center, it takes T/4. So to describe 30 degrees at the center, it will take T/12 seconds. It will take T/12 seconds, yes or no? You know what I'm saying? So the time taken by P to go from this point to this point is T/12 seconds. It's T/12 seconds, right? Because from here to here, it's T/4. And this is 1/3 this arc. This is 1/3 this arc. So to describe a length 1/3 the arc, the time taken would also be 1/3. So the time taken to go from P to P prime is going to be T/12. And for the oscillator, the time taken by the oscillator to go from the midpoint to the mean position is T/12. Know what I'm saying? So there is an oscillator at some instant, and A is the amplitude of this oscillation. Omega is the angular frequency, and at some instant of time, say the oscillator is at Q at a distance A/√2 from the mean position, and is heading leftwards, So if Q is heading leftwards, the corresponding point on the auxiliary circle would be P on the upper half of the circle, and P would be moving in this sense. P would be moving in this sense from this point onwards. Now, I want to find the time it takes for the oscillator to go from x equal to a by root 2 to x equal to 0. From x equal to a by root 2 to x equal to 0. Very clearly, that's the time taken by the corresponding point on the auxiliary circle to go from P to P prime, to go from P to P prime, yes or no, right? And in order to go from P to P prime, very clearly, this length is a unit, and this divided by this is 1 by root 2. This is 45 degrees. So this angle is also 45 degrees. Now to describe 90 degrees at the center, it takes t by 4 seconds. So to describe 45 degrees at the center, it's going to take t by 8 seconds. It's going to take t by 8 seconds. So then the time taken to go from P to P prime is going to be t by 8 seconds, and for the oscillator, the time taken to go from x equal to a by root 2 to the mean position, the time taken will also be t by 8 seconds. T by 8 seconds. It's as simple as this. So the whole idea of the auxiliary circle and the mapping onto the corresponding point on the auxiliary circle is to evade complexities involved in the motion of the oscillator, which is time varying acceleration, time varying velocity, in contrast to a simplistic motion offered by the corresponding point on the auxiliary circle, a simple benign uniform circular motion with constant angular velocity omega, right? So you understand this idea? Now, say there is an oscillator executing SHM between these two limits, executing SHM between these two limits. At some instant of time, the oscillator is at Q. At some instant of time, the oscillator is at Q. Let's say at an instant of time, T1, the oscillator is at Q. The and is moving leftwards, and is moving leftwards, and is moving leftwards. The corresponding point on the auxiliary circle is P as shown and moving in this direction. At t equal to t2 seconds, Q arrives at Q prime, and the and is still moving leftwards, and the corresponding point on the auxiliary circle is P prime. This is again T1 and at T2. Now, there is a certain angle described by the auxiliary particle at the center of this auxiliary circle. If you choose to call this angle delta phi, we then say that between two positions of Q and Q prime, the phase difference is delta phi. Between two positions of Q and Q prime, the phase difference is delta phi. Between two positions of Q. Now, if I have theoretically, if I have two identical oscillations executed by two particles executing identical oscillations, identical in respect of amplitude and frequency. Identical frequency means angular frequency. Two oscillators executing simple harmonic motion with the same amplitude and the same angular frequency omega. Say this was O1, the center of the mean position of one of the oscillators, and it was oscillating between these two limits. And there was another oscillator executing simple harmonic motion about O2, Again, same amplitude and same angular frequency, At some instant of time, so this auxiliary circle would be of the same radius equal to the amplitude of motion, right? At some instant of time, this oscillator is at Q, and is moving leftwards, right? Whereas this oscillator is at, say, P, this oscillator is at P and is moving rightwards, This oscillator is at Q and is moving leftwards, whereas this oscillator is at P and moving rightwards towards its mean position, right? But the quality of SHM executed by the two oscillators is the same, because the quality is determined entirely by two things, the amplitude and angular frequency, right? Now, these are their respective auxiliary circles. And this is the direction of motion and position of the two oscillators at the same instant of time, at, let's say, the same instant of time. Now, what we could do is, we could mentally imagine the following. I mentally imagine physically lifting this auxiliary circle and flushing it with this auxiliary circle But even before I do that, the corresponding point on the auxiliary circle for Q, is this, say Q prime, and is moving in this direction with constant angular velocity omega. The corresponding point for this P, will it be on the upper half or on the lower half? It's going to be on the lower half. It's going to be, say, P prime. It's going to be P prime. These are their corresponding points on their respective auxiliary circles. Right. Now, when we have to compare two identical oscillators, identical in respect of amplitude and frequency, then what we normally talk of in common parlance is the phase difference of oscillations. We say that P and Q differ in phase. These are identical oscillators, but they differ in phase. Now, look, if you go back to my first discussion on simple harmonic motion, I spoke of a phase. Which was about, at a given instant of time, the position of the particle and the direction in which it was heading. That determined the phase of oscillation. Right? Now, I'm not talking of an absolute phase, and an absolute phase was like an imaginary thing. It was an observer's perspective. It was simply an observer's perspective. But now, I would want to communicate the idea of the phase difference between the two oscillators P and Q. Given that they are identical in their amplitudes of motion and their angular frequency, I want to contrast and compare their phases. The phase difference is what I want to embark upon by means of this. Now, the phase difference between these two oscillators P and Q could be obtained when I mentally imagine physically lifting this circle and flushing it or dumping over this circle, so that it's as if I'm superimposing one circle over another. And now if I did that, it's like O1 would coincide with O2, O1 would coincide with O2, while Q would be here, Q prime would be there, and if P is here and is moving to the right, its corresponding point on the auxiliary circle would be here, and that would be P prime, and that would be P prime. Yes or no? Right? Now, the phase difference of oscillation is obtained. Join their corresponding points on the auxiliary circle to the center of the circle, which is the mean position, and this angle then is the phase difference between the two oscillators. This angle then, delta phi, is the phase difference between the two oscillators. This angle delta phi essentially is the phase difference between the two oscillators. Now, yes or no? Right? Makes sense to you? Can I write this off? Now, say, so every time I'm talking of two particles and I show them on the same, I show their corresponding points on the same auxiliary circle, it does not necessarily mean that they have the same mean position and the same limits of oscillation. It just means that they have the same amplitude and they have the same omega, but then I have flushed one auxiliary circle over another for the sake of comparison. Right? That's what I would mean at all times. Now, let's say if there were two auxiliary particles and the center of the circle was their mean position, amplitude A, angular frequency omega, and one particle was P and was moving in this direction, and the other particle was Q and was moving in this direction, Both were at the mean position, and headed in the same direction. Do you then realize that their corresponding points on the auxiliary circle P prime, Q prime would be at the same point? Their corresponding points on the auxiliary circle would be at the same point, P prime, Q prime, right? And these points would be moving in this direction, yes or no, right? And now, if you join P prime to the mean position and Q prime to the mean position, like I said, if P prime is here, Q prime is here, and this is the mean position O, then this angle would be the phase difference between the two oscillators, But in this case, what's the phase difference between the two oscillators? 0. Do you realize? I could mathematically conceive of the phase difference between the two oscillators P and Q to be 0. Are you all right with this? Right? Right? In fact, what could have also happened is this all right? At some instant of time, both, let's say both start to execute SHM at the same instant of time, t equal to 0, Q in this direction, P in this direction, and we readily say that the phase difference is 0, right? Now, in contrast, say at time t equal to 0, Q is headed towards the right and P was nowhere in picture. P was nowhere in picture. P did not prevail, right? So then the corresponding oscillator, corresponding point of the auxiliary circle was Q prime here, and it was moving like this, right? Q executed a full oscillation and came back to the mean position. Q executed a full oscillation and came back to the mean position. Now Q was here, reverting to the mean position after a full oscillation, after a complete oscillation, and was once again headed rightwards, right? Now in this time, what's the angle described by Q prime at the center of the circle? 2 pi. The angle described by Q prime at the center is going to be 2 pi radians. So Q prime would have described an angle 2 pi radians at the center. Q prime would have described an angle 2 pi radians at the center, right? And now at this instant of time, that is at this is time t equal to 2 pi by omega. At a time t equal to 2 pi by omega in a full time period. In a full time period, this gets executed. Now at this instant of time, another particle is set into motion. Another particle is set into motion. Call it P. There is another particle set into motion at t equal to 2 pi by omega. It did not prevail from t equal to 0 to t equal to 2 pi by omega. It did not prevail in this interval of time. But now all in a sudden, there was simple harmonic motion triggered into P, starting at the mean position and heading rightwards with the same amplitude and the same angular frequency. The corresponding point on the auxiliary circle P prime, then I can imagine then that this angle that it would have described would be 0, right? In this time, the corresponding point on the auxiliary circle would have described an angle 2 pi for Q, and for P, the corresponding point on the auxiliary circle would have not yet opened its account. Yes or no? It would have described an angle 0. So, but then if I start looking at P and Q, from this instant onwards, if I start looking at P and Q from this instant onwards, then I'll be compelled to claim and assure that the phase difference between them is 0. However, very mathematically speaking, the phase difference between them is 2 pi. It's about how much more the corresponding point on the auxiliary circle has described up to that instant of time. That's the phase difference up to that instant of time. So up to this instant of time, the corresponding point for Q would have described 2 pi and P would have not yet opened its account. Yes or no? Which means, mathematically speaking, phase difference is 2 pi in this case. Between P and Q, the phase difference is 2 pi. But physically, the phase difference is 0. Physically, the phase difference is 0, as we had seen earlier. Which means, a phase difference of 0 is the same as a phase difference of 2 pi between two oscillators. Between two identical oscillations, a phase difference 0 is synonymous with a phase difference of 2 pi. Right? And if the phase difference 0 is synonymous with a phase difference 2 pi, then I can even say that it's the same as a phase difference 4 pi. It's the same as the phase difference 6 pi. So in general, a phase difference 0 plus minus 2 pi plus minus 4 pi plus minus 6 pi, and in general 2k pi, a phase difference 2k pi would be identical for any k. If I talk of a phase difference 2k pi, then I can subscribe to any value, integral value of k equal to 0, plus minus 1, plus minus 2, etc. So phase difference 0 is the same as phase difference 2 pi, is the same as phase difference 4 pi, and so on and so forth. Right? what it really means is these are two oscillators, let's say this upper pen and the lower pen, and they are at their mean positions, right? Both executing simple harmonic motion with same amplitude and same angular frequency. At a certain instant of time, this is moving rightward and this is also moving rightwards. So they reach their amplitude position at the same time, they come back to the mean position at the same time, and they go to their leftmost amplitude at the same time, and so on and so forth, right? That means when you look from top, if they are executing motion like this, if you look from top, the motions are identical. They get completely synchronized with each other. These are two motions, simple harmonic oscillations in complete synchronicity with each other, right? Mathematically, I could say that, well, the phase difference between the two oscillators could be 0, or could be 2 pi, or could be 4 pi, or could be 6 pi. It does not matter. It's the same thing. A phase difference of 0, 2 pi. And whenever the phase difference between two particles is 0, 2 pi, 4 pi, etc., we say that the two particles are in phase with each other. We say that the two particles are in phase with each other. So whenever the phase difference between two oscillators is an even multiple of pi, we say that the two particles, the two oscillators are in phase with each other. Are in phase with each other. Their motions are completely synchronized. Their motions are completely synchronized. At any given instant of time, they would be at the same distance from their respective mean positions, heading in the same direction, executing simple harmonic motion with of identical amplitudes and identical frequencies, angular frequencies, omega. So this is what is meant by two particles, two oscillators being in phase with each other. That means it's about a phase difference being 0 or 2 pi or 4 pi or 6 pi. And are you fine with this idea or not? Right? Now, again, two oscillators, but then represented on the same auxiliary circle. The auxiliary circle is only a representation. I mean, they are actually independently executing simple harmonic motion along different lines, right? One particle is P, headed in the leftward direction, right? At a certain instant of time and at the mean position, headed in the leftward direction. Another particle is Q, at the mean position, but headed rightward at a certain instant of time. Now, their corresponding positions on the auxiliary circle would be, for P, it's going to be P prime like this, and for Q, it's going to be Q prime. What's the phase difference between the two particles? Pi, pi. Look at P prime, Q prime, and the angle that they together subtend at the center of the circle. So the phase difference between them is, you know what I'm saying? The phase difference between them is going to be pi. They are at these mean positions, but headed in the opposite directions. The phase difference is pi. In fact, we could have had P starting its motion at t equal to 0, but Q starting its motion at t equal to 2 pi by omega. We could have had P starting its motion at t equal to 0, P at t equal to 0, and was found to be moving leftwards, and Q was nowhere in picture. Q was nowhere in picture. So while P executed a full circle, the corresponding point of the auxiliary circle described an angle to pi radians at the center. Yes or no? Now, at t equal to 2 pi by omega, that means in a time when P would have described 2 pi radians at the center, the corresponding point on the auxiliary circle, the corresponding point on the auxiliary circle would be here. And it would be associated with zero description at the center. It would be associated with zero description at the center, right? So now, the angle that P has described by this point of time about O is 2 pi, right? And Q, the corresponding point of the auxiliary circle would have been 0. So do you realize that the phase difference is not just this pi, it's pi plus 2 pi. That's the phase difference between P and Q. That's the phase difference between P and Q. It's not just this 2 pi minus 0. In addition, it's this pi. Had they started at the same instant of time, it would simply have been pi. But now, P has 2 pi radians more credited to its account at the instant when P starts its motion. So the phase difference between them is not, mathematically, is not pi, but is pi plus 2 pi. So now the phase difference is 3 pi. The phase difference is 3 pi. We could have imagined Q to have started at t equal to 4 pi by omega. Then this would have been 4 pi, and then the phase difference between P and Q would have been 5 pi. The phase difference between P and Q would have been 5 pi, 7 pi, etc. Do you realize that a phase difference of 3 pi, 5 pi, pi, etc. is all the same. The phase difference of pi, 3 pi, 5 pi, 7 pi between two oscillators is all the same. Why? Because when at the mean position, if the two particles are observed at the same instant of time, P would be moving leftwards, Q would be moving rightwards, and the angle described here is going to be pi radians, which is the same as pi plus 2 pi, which is the same as pi plus 4 pi, which is the same as pi plus 6 pi, and so on and so forth. So in general, if I have two oscillators with phase difference an odd multiple of pi, with a phase difference an odd multiple of pi, we can imagine the motion to be as if both particles at a given instant of time at the mean position, one moving leftwards, the other one moving rightwards. That means moving in opposite directions, essentially. Moving in opposite directions. When at the mean position they are headed in opposite directions, we say that the two particles are out of phase with each other. We say that the two particles are out of phase with each other. A phase difference of an odd multiple of pi is like saying out of phase with each other. The two oscillators are out of phase with each other. Got me? Makes sense to all of you, right? So, if I have two oscillators, both at the mean position, identical simple harmonic oscillations, both headed rightwards, together they reach their amplitude positions, extremities together, their mean positions in the same direction, then we say that they are in phase with each other, and being in phase with each other is like a phase difference 0 or any even multiple of pi. Whereas if these are two oscillators, one is headed in the rightward direction, one is headed in the leftward direction, at a certain instant when both are at the mean position, we say that the phase difference between them could be pi or plus minus 5 pi or plus minus 3 pi, or in general an odd multiple of pi. The two particles then are said to be out of phase with each other. This phase difference is about two particles being out of phase with each other. Are you fine with the terminology in phase and out of phase? Being in phase and out of phase. Clear? In fact, it's very important that you understand everything that I'm saying, because this would be the foundation for a lot of serious discussions. So, don't feel feeble in these concepts. If you want me to reiterate any one of these things, I'll be more than willing to do so. But it's a simple little thing. But you need to have the right perception around it. Okay. say at a certain instant of time, Q was executing simple harmonic motion and was found here at t equal to 0. Right? And at t equal to t1, Q arrived at Q prime. Q arrived at Q prime. Heading leftwards, t equal to t1, Q arrived here. At that instant of time, at t equal to t1, there was another particle, call it particle P, at t equal to t1, that got inducted into simple harmonic oscillations. Right? Now, the direction in which P started to move was, say, leftwards. The corresponding point on the auxiliary circle for P, was, let's say, P1. The corresponding point at t equal to t1 for P was P1. The corresponding point for Q at t equal to t1 was, say, Q1. This was the center of the circle. Then again, the understanding that prevails in the mathematical community is that we say the particle P lags behind in phase compared to Q. We say that P, the particle P, lags behind in phase compared to Q. Now, the implication is how much behind? So if I have to compare the phase difference between two oscillators, then I look at the phase difference at the same instant of time. Well, the phase difference at t equal to t1, is delta phi. The phase difference between the two oscillators at t equal to t1 is delta phi. So we say that P lags behind in phase compared to Q by an amount delta phi. So in this case, now if at t equal to t1 the phase difference is delta phi, then at a later instant of time, a common instant t equal to t2, what would be the phase difference? It will still be delta phi. Why? Because the angle described by Q1 at the center would be the same as the angle described by P1 from T1 to T2. So the difference in angles will still be delta phi, right? So if delta phi is found to be the phase difference at a certain instant, then that phase difference is maintained at all instants, right? So it's not a time varying phase difference between two oscillators. It's a phase difference determined out of one set of data, and that phase difference is carried forward at all instants. Got me? So we say that Q is ahead in phase by delta phi, or P lags behind in phase by an amount delta phi. That's the understanding, right? Now once you've identified the phase difference between the two oscillators, say P lagging behind in phase by an amount delta phi compared to Q, then if I describe the motion of Q, I started with Q, right? Q was ahead in phase compared to P by an amount delta phi. And I said, well, the motion of P is simple harmonic with amplitude A and angular frequency omega, right? And if I have to describe the motion of P, then I can always start by describing the motion of P as Yp, or let's say Xp, X of P, as some A sine omega t. I can always assume that while it was at the mean position x equal to 0, that was t equal to 0. Who stops me from doing so? Right? Or rather, different observers will give you different values of phi for the same A and same omega. Therefore, there is nothing like an absolute phase. There is nothing like an absolute phase. So, let's say some observer put the motion of P as xp equal to A sine omega t plus phi, and he calculated phi on the premise of a certain position of P at a certain instant of time and its direction of motion. On these grounds put together, he computed the value of phi. Although there is nothing God sent about this phi, it will be different for different observers. But let's say for the same observer, it describes the motion of P as A sine omega t plus phi. Now, if he is given the task of describing the motion of Q, which lags behind in phase, compared to Q, or rather, this was the original one was Q, right? In the figure that I drawn. So Q. So now you are given another particle P. That lags behind in phase compared to Q. Another particle that lags behind in phase compared to Q. Then the motion of P is going to be described by A sine omega t plus phi minus delta phi. Instead of phi, you will have phi minus delta phi. Some other observer will give you phi equal to phi 1, then this will become phi 1 minus delta phi. The third observer will tell you phi equal to phi 2, then this will become phi 2 minus delta phi. So if the motion of one is described or patterned in a certain manner, the mathematical description of the other particle could be obtained given the phase difference between the two. So in this case, P lags behind in phase compared to Q by an amount delta phi. Is the idea understood? So in a situation which I described a little while ago, there was one oscillator which was, say, A sine omega t, phi equal to 0, say, okay, and another oscillator, so this is xq, another oscillator P, which was in phase with it, that means its phase difference with respect to Q would be in general 2k pi, k could be positive, negative, right? The motion of P is going to be A sine omega t plus 2k pi. So do you realize that these two oscillators are in phase with each other because the phase difference is an even multiple of pi. They are in phase with each other. Their motions are in tandem. They could be completely flushed one over another, right? Whereas, so this is being in phase, and if I have one particle xq whose motion is A sine omega t and another particle P whose motion is A sine omega t plus an odd multiple of pi, odd is 2k minus 1 to pi, then the phase difference between these two would be pi plus minus 3 pi plus minus 5 pi. That means these particles are out of phase with each other. All right. So this was more of a geometric understanding of a phase difference between two oscillators, and this understanding is terribly important. I hope all of you have registered the ideas that I have communicated. Even though these are simple ideas, I want them to be very clearly, transparently, and completely understood by all of you. Right? I hope the same has happened. Right? Stand by. Right. So by this time, you would have attempted some problems of this sheet titled discussions. Right? Now, just couple of uh, peripheral remarks, augmenting the things that we studied in our last class, right? The discussions that we had around the two block oscillator. Just few more remarks that could kind of complete the spectrum of understanding. One, which I may have mentioned before, but I'll reiterate. This was M1, this was M2, a collection of two particles. This was the center of mass. And in the ground frame, if M1 was found to have a velocity v1 and M2 was found to have a velocity v2, then the velocity of the center of mass was given by M1 v1 plus M2 v2 divided by, that was the velocity of the center of mass. Yes or no? Now this could be rewritten as M1 into v1 minus vcm. I transpose M1 into v1 minus vcm plus M2 into v2 minus vcm equal to 0. Collecting all terms on the same side, right? But v1 minus vcm is the velocity of M1 with respect to the center of mass. v2 minus vcm is the velocity of M2 as seen by the center of mass. Yes or no? This is v1 minus vcm and v2 minus vcm are the velocities of M1 and M2 in the center of mass frame reference, in the center of mass frame of reference. Yes or no? Right? So this is M1 and velocity of 1 in the center of mass frame plus M2 velocity of 2 in the center of mass frame. That's 0. So, which means if you have a collection of particles, then no matter what, if you calculate the center of mass, if you calculate the linear momentum of the system in the center of mass frame, if you calculate the linear momentum, this is the linear momentum of 1 M1 in the center of mass frame, this is the linear momentum of M2 as seen by the center of mass. Yes or no? Because V2Cm is the velocity of 2 in the center of mass frame. So these are linear momenta of M1 and M2 in the center of mass frame. Yes or no? Right? That means in the center of mass frame, the linear momentum of a collection of particles will always be 0. Indiscriminately, it's going to be 0. That's a very important thing. So the center of mass frame is a 0 linear momentum frame. The center of mass frame is always a 0 linear momentum frame. In the center of mass frame, if you observe a collection of particles, then the total linear momentum of the system as observed and reported by the center of mass observer will always be 0. This is a very important thing to understand, right? Not just for two particles, for any number of particles, the same result will hold good. Number one. Number two, even though in the ground frame the linear momentum was m1 v1 plus m2 v2 of the system, but in the center of mass frame it turned out to be 0, right? Another important remark is, again, there were two particles m1, m2, having velocities v1 and v2. In the ground frame, their velocities are v1 and v2, and the velocity of the center of mass in the ground frame is m1 v1 plus m2 v2 by m1 plus m2. Was the velocity in the center of mass frame? Now, evidently, like you can see, velocity of 1 in the center of mass frame is going to be v1 minus vcm. Is going to be v1 minus vcm. That is to say that v1 minus m1 v1 plus m2 v2 by m1 plus m2, which is like m2 into v1 minus v2 by m1 plus m2. The velocity of 1 in the center of mass frame is going to be the mass of 2 into v1 minus v2 by m1 plus m2. In a similar manner, the velocity of 2 in the center of mass frame, which is like v2 minus vcm, which will turn out to, instead of m2 you will have m1, and instead of v1 minus v2 you will have v2 minus v1. That's the velocity of 2 in the center of mass perspective, right? Now, both v1 minus v2 and v2 minus v1, the magnitude of these numbers will represent the relative velocity between 1 and 2, will represent the relative velocities between 1 and 2, yes or no, right? Now, if the center of mass is given the task of reporting the kinetic energy of the system, is given the task of reporting the kinetic energy of the system, and the kinetic energy of the system in the center of mass frame, the kinetic energy of the system in the center of mass frame is going to be half m1 v1 cm squared plus half m2 v2 cm squared. That's the kinetic energy of the system as seen by the center of mass, as seen by the center of mass. Now, which then turns out to be half m1 into m2 squared into v1 minus v2 whole squared by m1 plus m2 whole square plus half m2 m1 squared into, well, v1 minus v2 whole squared is the same as v2 minus v1 whole squared, so it does not matter when I square it, it's going to be the same, by m1 plus m2 whole squared. Yes or no? Huh? Now, if I take like a m1 m2 squared by m1 plus m2 whole squared, m1 m2 by m1 plus m2 whole squared common from this, m2 plus m1 into v1 minus v2 whole square. Yes or no? Right? Half, of course. What will be minus? Why? But when I square it, does it matter? We agreed this would have been v2 minus v1 squared, but that's the same as v1 minus v2 squared, right? So, in any case, this turns out to be half m1 m2 by m1 plus m2 into v rel squared into v rel squared. V rel is the relative velocity between 1 and 2, yes or no? Right? Hey, but have I given a name to m1 m2 by m1 plus m2? The reduced mass for a pair of particles m1 and m2. So, this is going to be half mu into v rel squared, half mu into v rel squared. So, if you have a pair of particles, then the kinetic energy in the center of mass frame, the kinetic energy in the center of mass frame is going to be half mu into square of the relative velocity. Now, relative velocity, whether you compute in the center of mass frame or the ground frame, is going to be the same, right? So half mu reduced mass into square of the relative velocity will give you the kinetic energy in the center of mass frame. It's an important thing to remember and know, right? Although in the ground frame, what would be the kinetic energy? Half m1 v1 squared plus half m2 v2 squared. In the center of mass frame, it's going to be half mu into v rel squared. Now, like I discussed in my previous class, say there was a mass m1, a mass m2, and in the ground frame they have velocities v1 and v2, and the spring is initially relaxed. Now, if the spring elongates or compresses, depending on, the spring will elongate if v2 is greater than v1. The spring will compress if v1 is greater than v2, but does not matter. It deforms, right? In a state of maximum deformation of the spring, their velocities must be the same. The velocities of m1 and m2 would be the same. This is what I told you in my last class. In a state of maximum compression or maximum elongation, the velocities of m1 and m2 would have to be the same. So, maximum, say, deformation by an amount x max. At that instant, they will have the same velocities, right? V and V, they'll have the same velocities at an instant of maximum deformation. Now, what I do is, I apply work energy theorem in the center of mass. Between these two states, state 1 and state 2, I'm going to apply work energy theorem in the center of mass. I apply work energy theorem in the center of mass frame. This was deformation 0. This was deformation x max. This was deformation x max. Very clearly then, work done by the spring force is going to be negative of the change in elastic potential energy, is going to be negative of the change in elastic potential energy. Potential energy of the spring here is 0. Potential energy of the spring here is half k x max square. Yes or no? And I repeat, I'm going to apply work energy theorem in the center of mass frame. So in any case, the work done by the spring force, is going to be negative of the change in elastic potential energy. That means this minus this with a minus sign. That means the work done by the spring force is going to be minus half k x max squared. That's the work done by the spring force. And that must be equal to change in kinetic energy, because I am applying in the center of mass frame, change in kinetic energy in the center of mass frame. Now, what's the kinetic energy in the center of mass frame here? 0. Because VREL is 0. Realize that VREL is 0. So, kinetic energy in the center of mass frame finally is 0. And what's the kinetic energy initially in the center of mass frame? Half mu, which is m1 m2 by m1 m plus m2, and VREL squared. VREL is v1 minus v2. So, VREL squared is going to be v1 minus v2 whole squared, right? So, work done by the spring force from work energy perspective must be change in kinetic energy in the center of mass frame. So final kinetic energy is 0 minus initial kinetic energy half mu into Vrel squared, where Vrel is the initial relative velocities of the two constituent masses connected by the spring. And that readily, so they would obviously give you V1 and V2, and then you can readily calculate the maximum deformation that is produced in the spring all time. So half kx max squared is half mu Vrel squared. Mu is known, Vrel is known, and x max could be computed given the value of k. Right? So this is applying work energy theorem for a two-particle system in the center of mass frame. So the important thing you want to remember is, in the center of mass frame, the kinetic energy for a pair of particles is going to be half mu into Vrel squared. Right? Now, let's look at these problems. SHM sheet titled Class Discussion. So we have problem 1. Spring initially relaxed, and this is V0, mass m, this is 2V0, mass 2m. This is mass A and this is referred to as mass B. So they are given impulses so that m and 2m acquire an instantaneous velocity V0 and 2V0 as shown. So the first thing we want to calculate the maximum stretch in the spring. The result that I just wrote. If x max is the maximum elongation produced in the spring, then half k x max squared be in the center of mass frame when I write work energy theorem. So I'm not repeating the same thing again. So half mu into Vrel squared, right? Where Vrel is how much? 3V0. Vrel is of magnitude 3V0 precisely. And what's mu? Mu is going to be m into 2m by m plus 2m, right? So 2m by 3 is going to be mu. 2m by 3 is going to be mu. So this would enable computation of the maximum elongation produced in the spring. This is writing work energy theorem in the center of mass frame, in the center of mass. That's part 1 of the problem. Now, listen very carefully to the next part of the problem. Maximum and minimum velocities of A and B in magnitude in the ground frame. What's the maximum magnitude of velocities attained by A and B during this motion in the center of not in the center, in the ground frame. In the ground frame, what's the maximum velocity, right? What I'm going to do is, I'm going to take care of this by looking at things in the center of mass. I'm going to solve the second part of the problem in the center of mass frame and make sure that you have registered all the ideas here, right? These are important notions and this problem will act as a mouthpiece for those ideas, okay? So first things first, if I'm looking at the center of mass frame, I will have to reduce these velocities to the velocities in the center of mass frame. So first thing that I'm going to do is to find the velocity of the center of mass, right? So the velocity of the center of mass is going to be 4mv0 minus mv0, right? That direction positive, this direction negative, divided by 3m. So mv0. So v0, velocity of the center of mass is v0, yes or no, right? Now I'm going to analyze the situation in the center of mass frame, and I told you in my last class that in the center of mass frame, both these masses will execute simple harmonic motion with omega equal to root k by mu. Root k by mu. Mu is the reduced mass, right? So let me reduce the masses, the velocities of m and 2m in the center of mass frame. So in the center of mass frame, the velocity of 2m is going to be 2v0 minus v0. The velocity of 2m in the center of mass frame at this instant of time is going to be 2v0 minus v0, that is v0. Velocity of A in the center of mass frame is v0. Velocity of this small m in the center of mass frame is going to be 2v0. This v0 minus v0, so 2v0 leftwards, yes or no? Are you fine with this? Right? So this is all in the center of mass frame. Now what's happening is, if you are observing from the center of mass, this is at the mean position. It goes to its extreme right. And in the center of mass frame, its velocity in the extreme right will become 0, right? Means the amplitude position of 2m. Again in the center of mass frame, this is the mean position of m, right? And it's going to its extreme left, and its velocity in the center of mass frame in its extreme left is again going to be 0. And the extreme right of this and the extreme left of this has to occur at the same instant of time, right? Because if it didn't occur at the same instant of time, you would find that the linear momentum in the center of mass frame will not be linear momentum in the center of mass frame will not be 0. If the linear momentum of one becomes 0 in the center of mass frame, then the linear momentum of the other one also has to become 0 in the center of mass frame. Yes or no? For the total linear momentum in the center of mass frame to be 0. In the center of mass frame perspective, both the masses reach their extremities at the same instant of time. Got it? Now, so in the center of mass frame, the velocity of this will become 0, right? Vb at the extremity. And the other extremity of this, velocity of A, will also become 0 in the center of mass frame. In a state of maximum elongation, when both have reached their right and left extremities respectively, right? So this is a state of maximum elongation. Yes or no? Now, when the velocities have become 0 in the center of mass frame, the spring cannot stretch any further, and the spring forces would compel the masses A and B to cave in. In the center of mass frame, they would now close in. Right? Eventually, and this was the relaxed state. Now, what's going to happen is, the spring in the center of mass frame again would come to its natural length, relaxed state. spring again in relaxed state. Right? Now, if the spring has come to its relaxed state, what would be the velocities of m and 2m in the center of mass frame? Tell me, what would be the velocities of m and 2m in the center of mass frame? Huh? Same, but in opposite direction. When it was heading leftwards, it was 2v0 now like this. But now, by the time the spring would have reached its relaxed state, mass m in the center of mass frame would have gathered a velocity like this. 2m would have gathered a velocity like this. Same as the original state, but oppositely direct. So then, again, also from conservation of energy, in the center of mass frame, the sum total of kinetic energy and elastic potential energies of the spring must be the same, right? So you would expect, and also the total linear momentum in the center of mass frame has to be 0. So commensurate with both these conditions, this would acquire a velocity 2v0 to the left, and this would acquire a velocity v0 to the left, 2v0 to the right, and this is v0 to the left. Clear? Now, velocity of any particle in the center of mass frame is going to be what? Velocity of the particle in the ground frame, which we say is the absolute velocity, say, plus, velocity of P, I'll write in the ground frame. Velocity of P in the ground frame, I would say, is velocity of P in the center of mass frame plus the velocity of the center of mass. Velocity of any particle, that is the absolute velocity, that is velocity in the ground frame, is going to be the vector sum of the velocity in the center of mass plus the velocity of the center of mass itself. Oh, no. Now, during this entire journey, so the whole thing would have shifted to the right, but the velocity of the center of mass in a situation of this kind remains constant, that is v0. Yes or no? In this case, we want to find a maximum value. This is continuously varying. But velocity of center of mass is not varying. Velocity of any particle in the center of mass frame is continuously varying, while the spring is waxing and waning. Velocity of the particle in the center of mass frame is varying, but the velocity of the center of mass is not. Velocity of the center of mass is remaining constant. So then, when this is maximum, velocity of a particle in the center of mass frame has a maximum, then this will have a maximum. Not only that, it's also about direction. Look, write down, so that it's not forgotten. To have a maximum velocity as seen by a ground observer, to have a maximum velocity as seen by the ground observer, two things must be guaranteed. Number one, the velocity of the particle in the center of mass, frame must have the same direction, as the velocity of the center of mass, One. Number two, the magnitude of the velocity of the particle in the center of mass frame, must be a maximum, What I mean simply is the following. These two vectors must be in the same direction so that they are as large as possible. Isn't it? Both are along the same line. So they must be in the same direction, not oppositely directed. Because we want a maximum value of this. They must be in the same direction, number one. That means if VCM is to the right, then we are looking at an instant when VPCM is also to the right. Right? Number one. Number two, if VCM is not changing with time, then this must also be a maximum. This must also be. So they must be in the same direction, and the magnitude of the velocity in the center of mass frame must be the largest it could be. When these two conditions are met, then the velocity from the ground frame will be the largest. Have you understood this? Huh? Now realize when the spring is stretching in the center of mass frame, the spring is stretching. The velocity of the particle while it's stretching and the velocity of the center of mass are oppositely directed. So during the stretch, a maximum velocity of this in the ground frame cannot be obtained, right? But then, when coming back to its relaxed state, the velocity of the particle is like this, and the velocity of the center of mass is also like this. Yes or no? Now, so between this state and this state, at what point is the velocity of small m in the center of mass frame the largest? In this state, because see, it starts from Vb equal to 0 and it goes to Vb equal to 2V naught. So between this state and this state, it becomes the largest here. And beyond this point, the spring will compress and this will become less than 2V naught. This will become less than 2V naught. Yes or no? Right. So which means during elongation, you don't have the maximum m available in the center of mass. But while it's returning to its relaxed state, and when the spring would have got completely relaxed, then this is the state where small m would have had a maximum velocity in the center of mass frame and also in the same direction as the center of mass. Yes or no? So this would be a point where the velocity from the ground of small m would be the largest. Yes or no? Are you there with me or not? So then, if the velocity of small m in the center of mass frame is 2V naught and the velocity of the center of mass itself is V naught, then what's the velocity of m in the ground frame? 3V naught precisely. This is the relative velocity plus the velocity of the observer. So in the ground frame, this is part for B, Vb max in the ground frame is going to be 2V naught plus V naught, that makes it 3V naught, that makes it 3V naught. Right? So the maximum velocity of B, magnitude of velocity of B seen from the ground is going to be 3V naught. Clear? The maximum velocity of A as seen in the ground frame. Yes, yes. See, first of all, for A, it has to occur when the spring is elongating, because that's when the velocity of the center of mass and 2m be directed same now. Which means during elongation, I'm going to find the velocity of 2m in the center of mass frame go from V naught to 0. Go from V naught to 0. So do you realize that the maximum relative velocity in the center of mass frame occurs at this point? Because from this point onwards, the relative velocity will diminish. Under the influence of the spring force, the relative velocity V naught will become less than this. Yes or no? So which means this is a state where a maximum relative velocity occurs in the same direction. So the relative velocity is V naught and it's the maximum in the same direction as the center of mass, then the velocity from the ground perspective of 2m is going to be v naught plus v naught, which is 2v naught. So then the for A, maximum in the ground frame is going to be 2v naught, because relative velocity of A in the same direction in the center of mass frame is highest at this point. Beyond this point, the relative velocity of A decreases. So relative velocity highest here, and therefore maximum velocity of A in the ground would be 2v naught. It's going to be 2v naught. Got me? Well, and by the way, they don't occur at the same time, right? Maximum of A is occurring at t equal to 0. Maximum of B is occurring when the spring is coming back, right? Yes or no? Now, minimum. What's the minimum? First of all, for minimum, at a point when the velocity is the minimum in the ground frame, the velocity of, let's say, A and B would have to be in a direction opposite to the center of mass, because the relative velocity has to be the lowest it could be. So it must be oppositely directed to the center of mass, velocity of the center of mass, right? Now, look, for B, while the spring is elongating from this state to this state, its velocity would be opposite to the velocity of the center of mass. Yes or no? Right? You know what I'm saying? So then, at what point? So it varies from 2v naught to 0. Relative velocity varies from 2v naught to 0. Do you realize that between these two states, the relative velocity must have become v0 somewhere? Do you realize if relative velocity is varying from 2v naught to 0, then somewhere between these two states, this state and this state, the relative velocity must have become v naught. Between this state and this state, relaxed state and elongated state, the relative velocity must have become v naught leftward somewhere. Relative velocity is continuously varying from 2v naught to 0. So at some point when the mass is here, the relative velocity must have become v naught leftwards. And at that point, if the relative velocity of m has become v naught leftwards, then add to this the velocity of the center of mass, then what would be the absolute velocity of this? 0. Relative velocity plus velocity of the center of mass, that's going to be 0. So the minimum velocity of B is 0 in magnitude. I mean, you can't have a magnitude less than 0. I do realize that the minimum magnitude of B in the ground frame is 0. Again, for 2m, minimum would occur again at a time when this is coming back. When this is coming back, that's when it will have a velocity opposite to the velocity of the center of mass, right? Now, in its journey from here to here, relative velocity varies from 0 leftwards to v naught leftwards. Yes or no? Its relative velocity varies from 0 leftwards to v naught leftwards. And do you realize that when it's v naught leftwards, when the relative velocity is v naught leftwards, then the velocity in the ground is going to be 0. So minimum of B in the ground frame will also be, obviously again they occur at different instants of time. Did it get very burdensome for you? No? You understood everything that I have said here? Huh? Alright, next problem. It's a very important idea to retain. Now, at time t equal to 0, m1 is given a velocity v1 leftwards, m2 is given a velocity v2 rightwards. The spring is relaxed. We want to identify a point P. We want to identify a point P which remains at rest just after t equal to 0. Just after t equal to 0, it remains at rest. First of all, I'll give you a shopkeeper's method for this. Shopkeeper's method for this. I mean, if 20 grams cost 2 rupees, 40 grams will cost 4 rupees. That's shopkeeper's method, right? And then I'll tell you the physics behind it. So this is end A and this is end B. This is V1 and this is V2. So if I choose, let's say, leftward positive, then velocity of the end A of the spring is V1. Velocity of end B of the spring is minus V2. Is minus V2. Yes or no? If I choose leftward positive, then this end has plus V1 and this end has velocity minus V2, right? Now, over a length L, the change in velocity is V1 plus V2. Do you realize that? Huh? Over a length L, the change in velocity is V1 plus. Now, what we want is velocity at A is V1, velocity at P is 0. Velocity at P is 0. So, this is the distance for this much change in velocity. So, what's the distance for change in velocity V1? From A to P, what's the change in velocity? V1. So, what's the distance required? This is the distance required for this much change in velocity. So, for a change in velocity V1, the distance required must be this. This is shopkeeper's method, isn't it? Proportionality. No? No? Confused, no? Little, no? Do you realize that from A to B, the change velocity changes from V1 to minus V2? This is A to B. Velocity changes from, this is B, V1 to minus V2. Yes or no? It becomes 0 somewhere here. At X, this is X. It becomes 0 somewhere here. Right? What's the change in velocity from A to B? V1 plus V2. And L is the distance you will have to travel for a change in velocity V1 plus V2. So, What's the distance that you will have to travel for a change in velocity v1? Into v1. Distance traveled is L for a change v1 plus v2. So for a change in velocity v1, you will have to travel this much distance. So this is x. Don't like. Didn't understand, no? What is L by v1 plus v2? Distance covered from A per unit change of velocity. Per unit change of velocity. Yes or no? So, for a change of velocity v1, what would be the distance? For a unit change of velocity, it's this. So, for a change of velocity v1, what would be the distance covered? X. No. Are you still lost? No. Didn't understand. Now understood. Okay. Now let me use some physics here. The other stupid thing you could have done is the following. This is x equal to 0, v is v1. At x equal to L, v is minus v2. You can find the equation of this line and find the x when v becomes 0. It's a freaking dumb thing to do. Don't do that, right? And you find the equation of a line and then put v equal to 0 and solve for x. When you could use a 20 gram, 40 gram analogy here, right? I would never do that. But in any case, let me look at it in a physics frame of reference. Okay. This is v1, right? Now this point P, for a short time dt, just after that, it remains at rest, right? So it's as if there are two springs from A to P. P is like fixed from t equal to 0 to t equal to dt. T equal to 0 to t equal to small time dt. P is like a fixed point. Okay. A has a velocity v1 to the left from t equal to 0 to t equal to dt, and B has a velocity from t equal to 0 to t equal to small time dt, v2 to the right. And it's as if this point P is fixed and this part of the spring has got elongated. As far as B is concerned, it's as if P is fixed and B has moved to the, this has got elongated, right? Conceive the whole thing as two springs. There is spring 1 from A to P, and think of spring 2 from P to B. Yes or no? So this length is x. Mentally imagine this to be one single spring, and this length is L minus x, another spring. Now in a small time dt, this is spring 1, this is spring 2. In a small time dt, how much would this spring elongate? v1 into dt is the amount by which spring will elongate, right? And therefore the force in this spring is going to be, let's say, K1 is the force constant for this length. K1 is the force constant for this length. So if this is the elongation in the spring, then K1 into v1 dt would be the force in this spring. Yes or no? And look at this spring. In the same time dt, how much will this elongate? v2 into dt. And for spring 2, if the force constant is K2, then the force in this spring is going to be its elongation into K2. That's looking at the two springs separately. Looking at the two springs separately, yes or no? But now, after all, this is one single spring. So the force in this spring has to be the same as force in this spring. When it's as if two springs in series, they must subscribe to the same value of the force. This must be equal to this. So K1 V1 must be K2 V2. And the K of a spring is given by AY divided by the length of the spring. Area of cross section, Young's modulus, divided by L will give you the K of the spring. So K1 would be AY divided by X. X is the length of spring 1 into V1. And for K2, it's AY, same A and same Y, after all, both the springs, divided by the length L minus X into V2. No? So V1 into L minus X is V2 into, you get X as V1L by V1 plus V2. Much ado about nothing. Right? Huh? Shopkeeper, no? That's what I told you. Some of you were giving me very dirty glances, and it didn't appeal to you at all to use, shopkeeper's method. I mean, it's best for a banya to use shopkeeper's method than to do bizarre physics around it when you can just use 20 gram, 40 gram analogy and do that stuff. But then, well, for your soul satisfaction, right? Can I wipe this off? This is the cable of the elevator, not part of the spring. And then, so during happy days of the elevator, the cable was intact, mg acting downwards, and the spring elongated by an amount x naught to counter mg. So x naught, the elongation in the spring, must have been mg by k. This is all fine, right? And then, God forbid, this snaps. One of the things that I need to tell you is, this is precautionary. Every time you enter an elevator, when it's about to close in and you push your hand and it goes back, there are sensors on the door and the door gets withdrawn, right? It always happens. It almost always happens. That's the warning. There are sensors here and sensors can fail. And I tell you, it's a real incident that happened. The sensor failed one time and it carried the hand away, it detached it from the body. So it's better to wait for another 10 minutes for the elevator to complete one full cycle and come back to you than lose your hand and lose your heart. Right? Okay, so coming back to the theoretical elevator, falling freely under gravity. Right? So the elevator frame of reference is an accelerated frame, falling down with an acceleration g. So in the elevator frame of reference, now in addition to the spring force, there is going to be So this was the natural length of the spring, and this length was x naught. So in the elevator frame of reference, the forces would be not just mg and kx naught. There is going to be a pseudo force mg upwards. Kx naught was balancing mg, all right, right? So now this mg balanced this mg. This mg balanced this mg. So there was an unbalanced restoring force directed towards the equilibrium position kx naught, proportional to this displacement. So the motion of m is going to be simple harmonic in the elevator frame of reference. It's going to be simple harmonic with amplitude x naught equal to mg by k, with amplitude x naught equal to mg by k. So in the elevator frame of reference, the motion of m is going to be simple harmonic, omega equal to root k by m, amplitude equal to x naught, which is mg by, right? Have you attempted 4? No? Attempted? Most of you, how many of you have attempted 4? Okay. Where are you sitting? Which problem are you sitting on right now? Huh? Everything else done? Very nice. Very nice. Yes. That's very impressive. That's very impressive. Congratulations. Uh, which problem are you guys sitting on? 5th, 8th, 10th, 7th. Right. Let me illustrate 4 to you then. Let me illustrate 4 to you. A particle of mass m moves on a horizontal line AB. Such that when the particle is at any point P, two forces act on it. Mg by A into AP towards A, and another force 2mg by A into BP towards B. Show that the particle performs simple harmonic motion on the line when released from rest at the midpoint of AB. Hey, first things first, when it's at any P, say I call A as x equal to 0. And B, AB is of length, so this would be A0, B would be A0, and there would be a point P, intermediate point P, which would be x0, right? A force acts towards A, which would be mg into AP, so mg into x by A, and a force acts towards B, which would be 2mg by A into BP. BP is going to be A minus x, BP is going to be A minus x. Say this is the x direction, positive direction of the x axis. So in general, the force acting on the particle at any P x0 is going to be 2mg by A into A minus x minus mg by A into x, right? So which is going to be 2 mg minus 3 mg by A into x. And I have told you in the past that f equal to c minus some kx is going to be a simple harmonic oscillator. Only thing is, its mean position will not be x equal to 0. Its mean position is going to be x equal to c by k. Force becomes 0 at the mean position, so its mean position is going to be x equal to c by k. So, this is simple harmonic oscillation. With the mean position now, x mean would be value of x for which this becomes 0, value of x for which this becomes 0. So, x mean is going to be 2a by, its mean position is going to be x equal to 2a by 3. The force constant for the oscillator is going to be this, 3 mg by A is going to be the force constant for the oscillator, right? So, the omega for oscillation is going to be root k divided by m. So, that's going to be 3g by A root k divided, this is k, 3 mg by A is the force constant for this oscillator, and root k by m is going to be the omega for the oscillation, and therefore the time period for the oscillation is going to be 2 pi by omega. Time period for oscillation is going to be 2 pi by omega. Got me? Now, it's also given that the particle, so we've already demonstrated that the motion is simple harmonic, because this is the force characteristic and this is the time period of motion, omega of motion, etc. Now, the particle is released from rest at the midpoint of, that means if it's at rest at the midpoint of AB, midpoint means A by 2, 0. It's at rest, and the equilibrium position, call it E, which is x equal to 2a by 3. If the velocity is 0 here, do you realize that this must be the amplitude position? This is the mean position where the force is 0. This is the position where the velocity is 0, and therefore this must be the amplitude position, and the separation between E and M must be the amplitude. So, the amplitude of motion is going to be 2a by 3 minus a by 2, which is like a by 6 is the amplitude of motion. A by 6 is the amplitude of motion, yes or no? Right? Okay. Which means the particle will move a by 6 units to the left, will move a by 6 units to the right of E, right? Now, the farthest to the right that it goes from E, F, farthest that it goes from E, F, is going to be 2a by 3 plus a by 6. A by 6 is the amplitude of motion. So, the farthest it goes from the mean position on either side is a by, right? So, that means the x of f is going to be 2a by 3 plus a by 6, which is 5a by 6, which is going to be 5a by 6, right? So, x of f and it's the rightmost extremity of the oscillator, it can't go further. So, this is the point closest to B, this is the point closest to B, this is how it could come close enough to B. It can't get closer than F, it can't get closer than F, right? So, then this is 5a by 6, this is A, so this would be like a by 6. So, its distance of nearest approach from B is a by 6, its distance of nearest approach from B is a by 6, right? That's how close it could get to B. Fair enough? Now, if the force towards A stops acting on the particle when it's nearest to B, that means at F, suddenly this force ceases to act. which means now when it's at F, the velocity is 0 because it's at the rightmost extremity of the oscillation. Velocity is 0, and the only force that would act from this point onwards is going to be a rightward force 2 mg by a into a minus x, right? So this would be an unbalanced rightward force 2 mg by a into a minus x acting. So despite the velocity becoming 0 at F, a rightward force of this magnitude would cause it to get drifted towards B, right? So this was B, and when it's at some intermediate point P, which is x0, the force acting, see, I hope you realize why it would move beyond F towards B, beyond F towards B, because now this force ceases to act. Under the influence of this force and this force, it was at rest at F. It was unaccelerated at F. But now at F, only this force acts, so it would drift to the right under the acceleration produced by this force, even though the velocity at F is 0. F, of course, is 5a by 6. Now, when it moves to the right at some instant of time, it's at x0, right? What's the acceleration at x0? The acceleration is going to be 2g by a into a minus x. Its acceleration at p is going to be force divided by mass. Its acceleration at any given x, where x is, of course, again measured from a. All this x is measured from a. So its acceleration at p is going to be 2g by a into a minus x, yes or no? Right? And if the velocity at p is v, if the velocity at p is v, then do you realize that this must be v dv dx? Acceleration is v dv dx, right? Huh? All that you need to now do is you need to find the velocity at b. That means velocity at x equal to a. Velocity at x equal to a is all that you need to do. So I would then write this as v dv is 2g by a into a minus x dx. Integrate both sides. When at f its velocity was 0, that means at x equal to 5a by 6, right? F is 5a by 6. At x equal to 5a by 6, velocity was 0. So at x equal to 5a by 6, velocity was 0. We need to find the velocity when x is a. We need to find the velocity when x is a. So when x is a, let's say the velocity becomes, can you integrate and solve for v from this? Right? Can I leave it at this point? Yeah. So this was the natural state of the spring. It moves under the influence of a rightward force F. After a while, when the mass gets displaced by an amount x, this was x equal to 0, the force acting on it is kx leftwards and F rightwards. So the net force acting at any given x from the natural state of the spring is going to be f minus kx. Motion obviously then would be simple harmonic. Motion would be simple harmonic with omega still being root k by m. But the equilibrium position will now change. The equilibrium position is going to be x equal to f by k. That's going to be the equilibrium position. X equal to f by k. Equilibrium position would be when f net is 0. That x will give you the equilibrium position. Yes or no? So this x will give you the equilibrium position, which means this was one state of the mass where the velocity was 0 and it was being acted upon by a rightward force. And then you arrive at a state where it would have gathered a velocity v, but f net is 0. F net is 0 means x is f by k. This was x equal to 0. This was x equal to f by k. Do you then realize that it's going to execute simple harmonic motion about this position? This is the equilibrium position, and this is a position of 0 velocity. So then this separation must be the amplitude of motion. This separation must be the amplitude of motion, yes or no? Now, if this separation is the amplitude of motion, then as far as the maximum velocity is concerned, it occurs at this position, right? V max occurs at this position, and what would be V max? Right? V max in this is given to be V, isn't it? Is given to be V, which would be omega of the motion, which is root k by m into the amplitude, which is f by k. And all that's required of you to do is find the maximum velocity when the force constant becomes 4k. That means you have a spring of force constant 4k. So if you have a spring of force constant 4k, then the maximum velocity, let's say, is v prime, and instead of k you will have 4k. That's all. Instead of k you will have 4k. Very clearly, v prime is, this is, sorry, this is 2k, na? Or 4k? 4k. So v prime very clearly is going to be v by 2. You can see that v prime is going to be v by 2. So how many of you got all 1, 2, 3, 4 and 5 right? All of them? 1, 2, 3, 4, 5 independently? Not 2, but 1 you got right. Very nice. Good. You also got everything right? 1 to 5. Do you realize, once again, in the just after we commenced our classes, and within 2 months' time, people were clamoring for simple harmonic motion at that point of time. Was it a viable proposition to teach simple harmonic motion in the right perspective? I mean, when you were not even comfortable with what center of mass is, some things you had mugged up here and there, and to really understand, they could force things down your throat saying x is a sine omega t plus phi, v is omega root a square minus a x squared, time period is 2 pi by omega. Could all be dumped on you, but it didn't make sense actually to cover simple harmonic motion just after we started, within 2 months, I know there was talk about simple harmonic motion. There was talk about gravitation school exam. We'll fail in school exams, and someone came down to me and said, tunnel build through and through, tunnel build across the earth. How do I establish that the motion is simple harmonic, etc.? It would have been such an unwise thing to actually, teach simple harmonic motion at that point of time. And I really don't understand why people don't resist in school. People means you people don't resist when they teach you things that are beyond you at that point of time. I mean, you just take it lying low and get hammered so badly. So most of you did that though. And you had very worried parents at that point. All of a sudden, someone who's getting like a 95 in boards, not even getting a 59 in school, seemed like such an ugly thing. It was not possible. Just not possible to that point. The potential energy of a particle of mass 0.1 kg moving along the x-axis is given by. Now this is like a very simple little situation. Washroom, yes. Stand by. So this is like 5x squared minus 20x. And the force, the conservative force, given the potential field, is minus du dx. So which is 10x minus 20. And the equilibrium position would be given by F equal to 0. So x equilibrium is going to be 0.2. 0.2 meters is going to be x equilibrium, right? I'm sorry, this is 20. So x equal to 2. X equal to 2 is going to be the equilibrium position. So option A, the particle is being acted upon by a constant force, Ramesh. The speed of the particle is maximum at x equal to 2 meters. Yes, because that's the equilibrium position. The speed is going to be maximum at x equal to 2 meters. The particle executes SHM. Yes. The K of the motion minus 10x plus 20. Minus 10x plus 20. The K of the oscillator is going to be 10. The K of the oscillator is going to be 10. So the omega of oscillation is going to be K by M. So 10 divided by the mass 0.1. That means 10 radians per second is going to be omega. And therefore the time period is going to be 2 pi by 10. That is pi by 5 seconds is going to be the time period. Pi by 5. Now, what do you do when you have multiple springs connected differently? When springs are connected in series or in parallel, which I have discussed in the past, right? In series, you will have 1 by k equal to 1 by k1 plus 1 by k2. You could replace k1, k2, k, etc. by one single spring with k equal to 1 by k, summation 1 by ki. And in parallel, the k equivalent is going to be k1 plus k2 plus kn, right? You recall that. But what in the event springs are neither in series nor in parallel? They are at an angle. They are at an angle, right? Let me illustrate a little bit. Say, this is one single spring. This is another spring. And a mass m. Third spring. Say these are identical springs. Say this is force constant K. This is also force constant K. And say this spring is force constant K1. And they're connected to a mass m here. Connected to a mass m here. say this angle is alpha, this angle is, and the whole unit is in equilibrium. The whole unit is in equilibrium. It means, this spring will have an initial stretch, this spring will have an initial stretch, and the vertical force of this spring, the two springs will have a vertical component. This spring would have got compressed. So, the upward force of this spring, all of it would counter the weight in equilibrium, right? So, this is in equilibrium. What we are interested in is what happens when you slightly deviate it from equilibrium position, what transpires. Now, in all these cases, in situations of this kind, they will always categorically mention that for very, very small displacements, after all, whenever you are initiating simple harmonic motion, it's about an equilibrium state from where you cause a deviation and then simple harmonic motion results, right? But in situations of this kind, they'll tell you very specifically that the displacement that you are initiating to further SHM is very, very small. And then consequently, what would be the time period of oscillation if the motion is identified to be simple harmonic for small displacement from the equilibrium position? Now, in this case, this is the line of symmetry. And say I cause a small displacement downwards from this equilibrium position, from the line of symmetry. Along the line of symmetry, I cause a small displacement x downwards. That means this point P, where the mass m is connected, this point P where there is a mass m, is pulled down by a small amount. So I'll draw an accentuated view of this. P comes to P prime. This is only an extended view, but this displacement is these ends of the spring will not change. This end of the spring will come to P prime, and same with this end of. So the two inclined springs would come along the dotted line, Now, you realize that if this x is very small, it's given to be very small, right? The motion will be simple harmonic, I repeat, only when this x is really, really small. Right? Only then the motion could be approximated to simple harmonic, right? So we will assume that x is like very small. When x is very small, P and P prime are really, really close to each other. And if this angle is alpha, reckon that this angle will also remain practically alpha. This x is very small, then the angle that this makes with the vertical will remain almost the same, right? So this angle is alpha, so is this alpha from symmetry. These are identical. Now, look at one of the springs, and I'll replicate matters for the other spring because they're identically disposed with respect to the vertical line, right? So this was the initial position of one of the springs. This was the final position of the other spring. This angle alpha, this also alpha. P goes from P to P prime, and let's say this is A. Do you realize that the spring gets elongated? And this angle is like theta which is very small, right? For if this x is very small, this angle theta, the angular deviation produced will be really small, right? This angle theta is going to be very small. So it's one thing, all these approximations I am explaining one time. Down the line, every time I come across a similar situation, you know, I'll jump steps. Right now, I'll tell you what exactly I'm doing, because this is the first time I'm doing these approximations for you, right? So this theta is very small because this x is very small. There is change in the spring length. There is a change in the spring length. So there is an additional spring force acting. There is an additional spring force acting. But let's first find out the change in the spring length, which will give me the additional spring force acting along the spring length, right? From P, if I drop a perpendicular, Q, if I drop a perpendicular, Q being the foot of the perpendicular, Q being the foot of the perpendicular, right? Then do you realize that this angle is practically zero? This angle is practically zero. So if this is 90 degrees, this angle will also be almost 90 degrees. APQ will almost be like an isosceles triangle. This is theta equal to 0. And if this is 90, this angle will also be almost 90 degrees. Yes or no? So APQ will be almost isosceles. APQ would be almost isosceles. APQ would be almost an isosceles triangle. Right? So OAP would be approximately equal to AQ, right? But AP is the original length of the spring. So AQ essentially simulates the original length of the spring. It's not the natural length, the original extended length. The original extended length is AP, which is the same as AQ. Do you then realize that the change in length is going to be QP prime? Because the original length of the spring was AQ, the final length is AP prime. So the change in length is going to be QP prime. The change in length of the spring is going to be QP prime, yes or no? No. Now, this is x, this angle is alpha. So this is x cos alpha. This is x cos alpha. QP prime is x cos alpha, yes or no? That's the additional length produced when this descends by a small amount x. The additional length of the spring is x cos alpha, yes or no? Right? So which means there is an additional force in the spring. If when this goes down by an amount x, the additional force in the spring was like a kx cos alpha, k times the additional change in length. K times the additional change in length would be the additional spring force, kx cos alpha. Right? And now, whatever you did for this spring would be true for this spring. So the additional force along this spring, when it descends by an amount x, is also going to be kx cos alpha. Is also going to be kx cos alpha. Clear? Now, the horizontal components of these forces would cancel off. Kx cos alpha, sin alpha, kx cos alpha, sin alpha, they would cancel off, right? Causing the mass m to not deviate laterally. There would be no lateral force acting on the mass m connected at P, because the horizontal components have cancelled off. So then, the vertical components of kx cos alpha, the two kx cos alphas would get added up, right? The vertical component of this kx cos alpha is kx cos alpha into cos alpha. The vertical component of this kx cos alpha would be kx cos alpha, cos alpha. So kx cos square alpha plus kx cos square alpha. So 2kx cos square alpha, 2kx cos square alpha would be the restoring force because of the inclined springs, yes or no? So at P prime, you have, when displaced by an amount x, 2kx cos square alpha would be the vertical restoring force because of the inclined springs. Vertical restoring force because of the inclined springs. But the vertical spring has also got displaced by an amount x. So it will exert an additional force k1x upwards. It's going to exert An upward force, K1x upwards. So then, the restoring force would be this plus this. The restoring force would be this plus this. So F restoring, when you displace it by an amount x from this equilibrium position, the restoring force is going to be 2k cos square alpha plus k1 into x. If I add these two, 2k cos square alpha plus k1 into x is going to be the restoring force, right? Which is proportional to the displacement from the equilibrium position. So the motion is going to be simple harmonic, provided x is small, because all these approximations will fail. If x is not very small, this angle will no longer be alpha, this angle will no longer be very small, and all the change in length that I have written as x cos alpha would be deemed unfit for use. Got it? So F restoring is this. So for this system, the motion of this particle m connected at P is going to be vertical and simple harmonic, with the equivalent force constant of motion being this being the equivalent force constant of the oscillator, right? So root this divided by m is going to be the omega of oscillation, right? So the omega of oscillation is going to be root time period is going to be 2 pi by omega for small oscillations, Yeah. It makes perfect sense to all of you, right? So whenever you have inclined situations, inclined springs, when you can neither convert them into springs in series or springs in parallel, then there would be semblance of symmetry somewhere. Along the line of symmetry, a simple harmonic motion would be proposed on almost all occasions, and you can use approximations of this kind or similar approximations depending on the situation, and have your equations written down commensurate. This is what you do, right? So when springs are inclined, this is what is to be done. Suppose realize that the motion is going to be bizarre, absolutely horrendous. Not really so, but at least at this level it will look horrendous. In case these two springs were not identical, in the case this was K and this was K1, the horizontal forces will not cancel off. And if the horizontal forces will not cancel off, this particle would be subject to, in addition to a vertical force, an unbalanced horizontal force. So the motion of the particle then would be very, very sophisticated. But they would at this level give you things that look like this, almost like this. I mean, they might change the angles and so on and so forth, but essentially this, right? See, now after the inputs that I have given to you on this, you should be able to solve 7. 8 is not simple harmonic, but would be periodic. Will not be simple harmonic, but would be periodic. Come down, go up, come down, go up. If T1 is a time taken to fall down the plane, then 4T would be the time period. T, 2T, 3T, 4T. This T, 2T, 3D, 4T. That's how it's going to happen, right? I'll leave the sheet at this point of time. The only thing that I want to ask you is, are you familiar at least a little bit with equating moments of forces? A little bit? Huh? Can you calculate moment of a force about a point? No, no. So then, if that's the case, then 10 may not be your cup of tea. Sumit, stand back. Sheet गुलो नहीं है. You know, if there is a certain y that varies with x, this is x equal to x1 and this is x equal to x2. And now between x1 and x2, they say find the average y. Find the average y between x1 and x2. What it really means is, if this is an average y between x1 and x2, right? This x is y is continuously varying with x. And if this is an average y between x1 and x2, then average means that this area must be the same as this area of this rectangle. This is y average. The so many y's that you see here, if this is the y average, then the implication is that the area here must be the area there. Now, in calculus, we're going to learn, though much later, that if this y is some function of x, y is some function of x, which it is, right? Then this area from x1 to x2, this area from x1 to x2 is going to be given by integral fx dx. X runs from x1 to x2 would give you the area, shaded area, fx dx, x1 to x2, which in turn must be equal to y average, which is this height into the length, which is x2 minus x1. So we then say the average y in the interval x1 to x2, the average y in the interval x1 to x2 is going to be where y is fx, where y is fx. That means the average value of fx. This is the average value of fx. The average value of fx in the interval x1 to x2 minus x1. That's the average y in a certain interval, x1 to x2. Now, when they say, well, kinetic energy in an oscillator, let's say, going as x equal to a sine omega t, going as x equal to a sine omega t, at any given x, kinetic energy at any given x is given by half m v squared, where v squared is omega squared into a squared minus x squared. That's a kinetic energy at any given x, right? So now if someone says, what's the average kinetic energy when x changes from x1 to x2? What's the average kinetic energy when x changes from x1 to x2? That means average kinetic energy, which is written like this. When x runs from x in the interval x1 to x2, average kinetic energy in the interval x1 to x2 is going to be integral kinetic energy at any given x dx. X runs from x1 to x2 divided by x2 minus x1. Right? If someone says, what's the average kinetic energy when the particle goes from the mean position to the amplitude position, from the mean position to the amplitude position, then x1 would be 0, x2 would be a. This would be a minus. That would be the average kinetic energy over the space mean position to the amplitude position. Sometimes they would ask average kinetic energy in terms of time when t changes from t1 to t2, when t changes from t1 to t2. So kinetic energy written as a function of time. Kinetic energy written as a function of time is going to be half m. V is a omega sin omega, a omega cos omega t, a omega cos omega t. So a squared omega squared cos square omega t is kinetic energy as a function of time, right? And when they say what's the average kinetic energy in the interval t1 to t2, that means now this is averaging over time. This was averaging over space. This was averaging over space. Now if we want to average over time, right? So the average kinetic energy when t changes from t1 to t2 is going to be t1 to t2 half m a squared omega squared cos square omega t dt divided by t2 minus t1. That's the average kinetic energy. That's the average kinetic energy in the interval t1 to t2. So if in my previous sheet you've encountered some problems on these averages, space average and time averages are different things, right? So this was like a space average, this is like a time average, right? So this is what you do if you want to compute the average of a space varying or a time varying entity over a space period x1 to x2 or a time period t1 to, right? So the problems that you see in my previous sheet would be about this. Now you'll be able to do that. Do you have school tomorrow?